Okay, so now we will solve this problem. This is a internal flow problem. You can see, let's read the question at first. Consider water flowing through a 2-meter diameter pipe with a velocity of 10 meter per second. So this is, you can see the schematic. This is the inlet, this is the outlet. You can see the flow trajectories. So flow, the water is going this way, 10 meter per second velocity. The diameter, the pipe diameter is 2 meter. So now we need to calculate the Reynolds number and the flow behavior. So what we'll do is, we'll do the same thing like what we did for the previous problem. Here we'll write down the assumptions. So let's say this is a steady flow processes. So flow is not changing with the time, and the properties are constant. So we'll say properties are constant, right? Okay, so in this case we will actually consider the the 25-degree temperature. The water temperature is 25 degrees centigrade. So we know, if we actually want to calculate the Reynolds number, and then if we want to discuss the flow pattern, then we must need to calculate the Reynolds number. So when we'll start with the analysis, we know the Reynolds number definition. So the Reynolds number definition, we can write two different ways, like rho v. Here this is a pipe, we have the diameter. So instead of L or X, length or distance, we'll say diameter here, over dynamic viscosity. Or we can write what we did previously, Vx over kinematic viscosity. So as we know the diameter here, because this is a circular pipe, so that means we actually do not need this. Okay, so forget about this definition. So that means what we need from this formula is, we need the density. We have got the diameter, we have got the velocity. What we don't know is the dynamic viscosity. So here you will see the table. At 25 we said the properties will take 25 degrees centigrade. So you'll see the dynamic viscosity. If we go this way, here you see this is actually the dynamic viscosity. So we'll extract this value from here, and the other thing we need is the density, the rho. Actually, by using these two values, density and the dynamic viscosity, you can get the kinematic viscosity. We know the kinematic viscosity, it is equal dynamic viscosity over density. So if you want, then you can do that. Anyway, so for this problem, I'm going to actually write down or extract these two properties from the table. So I'll write it down here. So for properties, the density, we have got the density is 997 kg meter cube, and the dynamic viscosity is 0.891 10 to the power minus 3 kg per meter second. So it is actually at 25 degrees centigrade temperature, right? So now write down the Reynolds number. So it is rho v t, and the viscosity. Density is 997 kg meter cube. The velocity is 10 meter per second, and the diameter is 2 meter, over it is 0.891 and 10 to the power minus 3 kg per meter second. Use your calculator. It will be kind of the value like this, which is greater than 2300. So definitely, as it is much significantly higher than that, I just put some random values. That's why I have got some digit like that, but in practical problem we will get more realistic values. But here this is just for the demonstration purpose. So what we have got here is this value, it is actually significantly higher than this critical value, so we can say the flow is turbulent. So we'll discuss a bit more during the lecture. We'll try to connect this sort of problems with the real life applications, and then we will be able to understand, okay, what's the practical applications of this Reynolds number and how you can use it in different real life situations. So that's it for now. We'll discuss it during the lecture.